Guten Morgen, good morning, and welcome to the 2026 ISC Jack Dongarra Early Career Awards. My name is Michela Taufer. I am the Mathworth professor at the University of Tennessee, Knoxville, and it is my pleasure to chair this session today. As you may know, the Jack Dongarra Early Career Awards recognizes a rising leader in our community. We are recognizing our colleagues not only for their technical contribution, but also for the innovation, the impact, and the potential to impact our field of high-performance computing for a long time in the future. Before to announce the winner, I would like to invite Jack to join me on stage. Jack and I are very, very grateful for the contribution of 9 amazing colleagues and experts in high-performance computing. They didn't have an easy job this year because we had 11 very competitive candidates. Well, thank you so much to the committee, and thank you to Jack, who has been guiding us and leading us in this very challenging selection. And I'm very pleased to announce that the Jack Dongarra Early Career Award goes to Devesh Tiwari. So we are looking forward to your lecture.
Thank you, Michela, and thank you, Jack. I'm deeply honored and humbled by this recognition, and I would like to sincerely thank Michela, Jack, and the award committee for this honor. And just in case you're wondering, this is the same Devesh, it's the same shirt, it's just the top is different. That's what HPC does to you. So before actually I begin today's talk about staircases and trampoline, I want to say that I'm only just the speaking head. This award recognition truly belongs to an army of people, including my wonderful students, collaborators, family and friends, mentors and sponsors. This is really where the award goes. I'm just the speaking head. I want to give a special shout out to my wonderful students for their high-quality work and their commitment to excellence that is reflected in this talk, in this award, and in my career throughout. I'm deeply, deeply grateful to them. And before I begin, I want to say something about Jack. He may find it embarrassing, but I will just say it. Research communities have papers, ideas, proposals, talks, and that's what really drives science forward. And they always have, but how far a really community goes is really determined by who are the truly inspirational leaders, who are the thought leaders. And we are very lucky to have Jack, and that's why HPC has come so far. And I know when I say this, I represent many of us, that Jack has been that true role model for all of us, especially for me. Thank you, Jack. And I knew that given the wide gap between my intellectual ability and Jack's sheer brilliance, I always wonder if I will ever get associated with Jack. So this award is probably the easiest way to get associated. So thank you, Jack, again. So, as some of you know, my talks are usually based on 3 themes: quantum, HPC systems, resource management, community and collaboration. Community and collaboration is something that is really, really deep, close to my heart. And I deeply care about it, and I usually talk about it. But today's talk, actually, as I was beginning to prepare this talk, I started thinking, okay, what is this talk really for, and what is in it? Especially given that there are 2 technologies that are actually disrupting our community, computer science research in general. One is AI. AI is here. The other one is quantum. And quantum is always here and always in the future, both at the same time. in the quantum way. So what I realized was that this talk is really for maybe first year and second year PhD students who are or early stage graduate students who are really thinking at this time, what should I really work on? What really matters? Whatever problems should I work on? So I decided that I will rather have this talk based on 3 themes that have been very close to my heart, that has inspired me, and they are curiosity, purpose, and the third one is cricket. And I know you will say, well, cricket is just a sport. What is this doing in an academic talk? Well, cricket is a sport, but I will connect to you later. It has a deep connection with science and curiosity and the way actually community is built. So when I come to that, I will talk about it. Let me begin with curiosity first. Let me ask you a simple question. How many of you actually recognize 142,857? Okay, let me give a hint. How about this? 0.142,857, 0.142, and it repeats. I can see that this talk is truly for second-year graduate students because they are likely Gen Z, and if you're not Gen Z, if you're like me, you'd actually seen this number maybe as an approximation of 22/7. Actually, the decimal part is actually 1/7. Of course, the correct approximation that Gen Z uses for pi is actually 3.1415. But what I really want to emphasize this is such a simple number, 142,857, and it's just not my favorite number. It's actually favorite number of many mathematicians. It turns out it's a very beautiful number. And people have been so curious about this number that they found multiple properties of it, self-repeating. If you multiply by 1, you get the same number, of course. 2, the number rotates. 3, again, the number rotates. 4, number rotates. Of course, if you do 7, then you get 999. Not just this. You multiply by 8, you have a number, it breaks into 2 parts, you add them up, you get the number again. You multiply by 15, this is just an example. You can do this multiple times, you can take a square, again you add them up, you get the same number. The reason I mentioned this is actually where curiosity can really drive you forward. And not only this number really knows where to hide, where to go, including Jack's PhD thesis, where he was calculating eigenvectors, and here is that number hiding. It really knows where to go. Well, and pi is also something that you express your angles from 0 to 2 pi. I have Hilbert space here, so you know where I'm going with this. That's right, quantum computing. So if you thought a researcher will actually get up here and not talk about their research, thank you for letting me trick you for a few minutes. I will talk about quantum computing next. So when we actually started quantum computing, it started with a very, very simple sort of curiosity. Given a quantum computer we have today, and they're programmable, you can actually run real things on there, but what about answer quality? Answer quality is almost terrible. So for example, for very simplicity, you see the ground truth in black, and yellow is what you will actually get if you ran on a real quantum computer a few years back. So our goal was actually, how can we use HPC? Given my background was in HPC, I wanted to figure out how could we actually use HPC to make this better and actually build a system software stack for quantum computers. So I will actually talk about 3 things. Before I begin that, I also want to say when we actually started, most of the community, quantum computing community, had this belief that if you have a quantum computer, you should simply run on the best qubits and forget about the erroneous other qubits. All the qubits are erroneous, but some are more erroneous than others. And the current, at the time, people said, well, if you have less erroneous qubits, just use them and throw away the rest, or don't map your program there. And we said, we will actually simply challenge that conventional wisdom. And the way to do that is actually using HPC. So one, and again, I will talk about quantum computing, but I promise I will not make you go through any equations or any quantum computing background. Rather, I will summarize some of the works in a very intuitive way. Hopefully, you can remember those key insights even after this talk. So first one is Veritas. And by the way, HPC community has been very welcoming to early ideas. At the time we started this, very few people were working on quantum computing in this HPC space, and the space was actually very welcoming. They realized that this was a very good use of HPC. By using classical pre-processing and post-processing, you can figure out which qubits to map to. And we said, don't just use the best qubits, but rather figure out what happens to the error rate. So if the error rate actually has a lot of variation, you just don't want to map on the best qubits, but also figure out, even if they are the best qubits, if they have a lot of variations, what I call mood swings, you don't want to map on those things. Or if you map them, you do some post-processing to get rid of their mood swings. The next one, we actually, in quantum computing, any operation is reversible. So if you reverse the operation, you get the identity back. We said, well, we were just curious, and we said, what if I just reverse the whole circuit? What will be my program? And it turns out, if you do that, you can figure out the correct output, but it will require a lot of classical processing. So in Craft, we actually built an AI model on the classical side to figure out the correct output. Next was Quest, where we actually break the circuit into multiple pieces. And for each piece, we synthesize the circuit, approximate it on the classical side before running on the actual quantum computer. Again, if you have a very large, deep circuit, which you cannot run on a quantum computer, today, what you can really do is you can break the circuit into multiple pieces and then approximate each piece and then tie them back together, have a theoretical guarantee that this is how much your error will be, and then you run that on the machine. As I promised, if you don't remember all the details, three key insights are, take care of the mood swings of the qubits using HPC resources, just reverse the program and inject reverse gates. And the third one is, if the circuit is too large, break into pieces and approximate the pieces and then add them back. The second theme, which Martin also talked about yesterday in his keynote, he said, heterogeneity is going to be here, and I go one step further, and I say, even in quantum, there is going to be heterogeneity. There are going to be multiple types of superconducting, trapped ion, neutral atom, photonics, and so forth, which will actually all will be used because they all have different advantages. For example, neutral atom is, you can operate at the room temperature and you can move atoms around. Photonics is best at connecting two different quantum computers. So again, we actually did for neutral atom, for example, Geyser, we designed a new compiler framework which actually takes a circuit and extracts 3 qubits out of it rather than just 1 or 2 qubit and builds those 3 qubit gates. In Graphene, actually, we show that given your application, how you arrange your atoms is really important, which something that you cannot do in superconducting. In photonics, we actually figure out the way to train a machine learning model is figuring out which output states are equally affected by your photon loss. Again, as I promised, the key to remember is 3 atoms come together, rearrange my atoms for my application, and figure out if lighting is striking, photon loss is happening, which 2 output states are actually equally affected. If you can figure that out, you can train a really good model. And last one, which is very close to my heart, and I have been, my group has been focusing a lot on this, is actually showing that quantum computer has high utility on current applications. The quantum machine learning, again, natural language processing, including partial differential equations. The equations is actually gone here. We just had in Physical Review A, this published this month, where we actually show that you can do PDE on a real quantum computer. OK, the second one is about purpose. And this is, again, as we often discuss in the group, whatever we are doing has to have a purpose. And the purpose, even if it's computing and you think it's just coding, the purpose is following. You have, if you look at the data centers today, and this is a very use-centric view taken from our paper in SC25, the HPC power consumption over different states approximated. Then water scarcity, which says not all water is equal. So 1 liter of water in Texas may be different than 1 liter of water in Arizona or Massachusetts. And then on the very left, you have carbon intensity. If you look at it, it's very clear the way we are placing our data centers is probably not the most environmentally sustainable and conscious. So the issue is that if you look at it and you say, well, I can have this clean energy, and then it doesn't really matter because I'm done. I have clean energy. The issue is, how do you generate that energy? That energy generation itself may require water and may actually put further stress in the area where you are located. And that's why water scarcity is a very important aspect. And it's just not us. If you look at the news, and we started this 3-4 years back, but if you look at it in the last 1 year or even 6 months, communities have been saying, we don't want data centers. There are town hall meetings which go from 7 p.m. to 4 a.m. in the morning, and at 4 a.m. they vote and they say, we don't want data centers, because it actually has effect on our air pollution, water, health. It's going to take actually fresh water from our river and so forth. In fact, there are farmers in the Midwest in US who are saying, we don't want to sell you the land, even if you give us 20x more money than what the land really is. And this is where the purpose comes in. If 20 years back, if you told somebody, well, I'm studying computer science in an airplane, you're sitting next to somebody, they will give you happily their laptop or iPhone, and they would say, we trust you, can you fix this? Today, while they use ChatGPT, they might say, oh, you are the one who is building these data centers and taking our water away and their energy away. This is our community. We don't want to be remembered like that. We want to say, we are bringing enormous good, and what can we really do about it? So my point is not about whether we should build a data center or not. My point is, can we build the data center in a way that communities can trust and say, yes, this is for our good? So what we have been doing is, we have been building, the first step that we took was building the modeling frameworks itself. How do you model carbon footprint? How do you model water? How do you model forever chemical impact of the data center? So, for example, carbon, energy, water, or PFAS, how do you model them? And the reason these frameworks are important is they let you actually decide when should you upgrade your supercomputer. What are the factors that decide that? Can actually modular reactor help you get rid of your carbon emission problem? And the short answer is no, because they have a lot of water impact. What about the PFAS burden and so forth? The other thing that we have done, and again, I will go through quickly through this, actually very simple techniques, which is just mixing multiple generations of hardware can really save a lot of carbon emission. Deciding how do you do on-site and off-site water allocation can actually save you significant water, or if you decide to defer the job. Finally, one thing that we have actually shown is if you reshape the user behavior itself, when they perform certain queries, you can again save significant both carbon and water. The reason I mention this is because energy, water, carbon, they are very appealing, but they're not performance. So we have to become really creative, and we have to give people incentives to actually change their behavior so that we can save water and carbon. And that's why I think it's very important. The slide is slightly crowded, but we started in 2020 where we said we have to give incentive to people to change their behavior. For example, in Gift we show you can get more additional compute hour if somehow for a moment you can actually trade off your I/O bandwidth to somebody else. Shout out to Riken for actually doing this Fugaku point incentive where they actually let users reduce their power consumption, or users who actually have lower power consumption have lower queue wait time. This is a collaboration with Riken and Sandia. And finally, I want to talk about Cricket. And I know I have a few minutes left. Let me just. Okay. So Cricket is actually a game, and I want to give a very brief background, and I'm taking this because I know if I talk in South Asia, every 10 seconds you will be interrupted and corrected if you talked about cricket. So I know I have the microphone, nobody will correct me, so I can say whatever I want to say, which is cricket was actually born in England, in UK, played with love in South Asia and with rigor in Australia and New Zealand. In fact, my friends in America are learning, and in LA 2028 Olympics, cricket will actually debut. There are three, and this may look digression, but you will see why this is so important. Cricket was actually a five-day game. Not a 3-hour, not 8 hours, 5-day game. Every morning you wake up, from 9 a.m. to 5 p.m. you play it for 5 days. Every day the pitch actually changes. So the skills that you need to play and play really well changes every single day. And you really have to persevere. You need to have a lot of rigor. Over time, what really happened was the incentives were different. They moved to the very shorter format, 3 hours. And the players are now incentivizing short-term skills, playing really well, but very short amount of time. And that's what, in some sense, it has parallels with what AI is doing and what it will do to science. And this is not necessarily a bad thing. There are all kinds of players, and they're really good. But when this change happens, it's very troublesome. And really confuses a lot of players and scientists how they should adopt. I'm going to talk about AI in that aspect. This is what I call AI's Kijaki box. Kijaki is a Japanese term which says early signs of great things to come. On x-axis, I show time, and y-axis, I show performance level, so to say. And then traditional humans, if let's say they're learning biology from 1st grade to 12th grade, and then they go to college, they achieve some sort of high expertise. And super expertise, what I call is, solving a multiple-decade open problem. So few humans do that. Normally, not all humans can do it. What really AI will do is, it will actually make you get to that high expertise really fast. That's what I call a steep jump. And then there would be AI tax. AI tax is there would be a lot of fluctuation, because it depends how you used AI to learn those skills. Did you learn the fundamentals and first principles correctly or not? So this is why I call fluctuation, and you will see the average maybe actually right just below high expertise or above. We don't know that yet. The other thing that AI will do is, and this is one of the biggest arguments, is that you can pursue multiple things at the same time. So the same human can have biology expertise and chemistry expertise in a very short amount of time, get to this steep jump. But in my opinion, this Kijaki box is just a Kijaki box, yet not fully open, because what will really happen is we will have these performance levels, which will be fluctuations. So I call them periodic sparks, but no continuous light. And I want to pause a moment and say, while we have access to AI, and by the way, Bloom had this paper in 1984. He calls this 2 sigma Bloom effect, where he says if you have a tutor, personal one-on-one, you are likely to have a very better performance than an average. And AI can actually have that, but despite that, we will not have this. And the reason I believe it will not happen is because there is something really hidden in traditional humans, which is invisible hands of other humans. That is discipline and the motivation that they provide. AI, as far as we know yet, doesn't provide that discipline and motivation. And this is why this is such an important thing. And I think human-guided discipline, and this is why, again, it's the coaching, I go back to cricket analogy again, because the coaching, the mentorship, which is really going to inspire people, and this is how they achieve high expertise and remain there and not fluctuate. So this will be the most critical aspect of AI's Kijaki box, and also reducing AI tax. I think if we do it right, and this is the community which can really do it right, we will actually reduce the AI tax, and you will see some humans can even breach super expertise. That's what I believe will happen if we did the motivation, discipline, and inspiration right. So a lot of students also have been asking, well, this is good, but AI really makes me anxious. What kind of problems should I be working on? I imagine them in two axes. One is cognitive burden, and the other one is intellectual challenge or creativity, from low to medium to high, and from low to high. I believe, and this is my speculative personal opinion, AI will be probably really good if the cognitive burden is very high and intellectual creativity needed is low, or the cognitive burden is very low and the intellectual creativity is also low. But when the cognitive burden is very high, much higher than what humans can really do, it should really be driven by AI. So choose problems. If you choose a problem which has a very high cognitive burden, you simply go to that problem, let AI drive it, and then you provide your human expertise. On the other hand, if the intellectual capacity needed is very high, for example, solving a proof, it should be driven by a human, but assisted by AI, which has also been shown recently in Erdos conjecture disproving. And again, this is my speculation, but this is very particular to HPC. I believe as we work on these problems, people often ask, well, what will happen to research publications and so forth when we can generate them so quickly? I think what will really happen is we'll actually have hackathons, just like we have student cluster competition. So HPC community has known this for a very long time, and people will be less worried about powers, but rather more worried about actually what is the problem statement. So since I have less time left, I would like to go to the last part of my talk, which is talking about perseverance. I just want to remind you again that there are 3 forms: Test cricket, one day, and T20. And I want to simply say that this is a player which you may not recognize, but he's like how Jack is to HPC. He's god of cricket, god of HPC, Sachin Tendulkar. He actually had to wait for almost 20 years to get his first World Cup, and the only World Cup. Rahul Dravid, he actually played in a very different format, and he actually coached the team in a very different format in T20 where you won the World Cup. So your best may come actually in a format where you least expect. So lose yourself in serving others. This is a person whom we don't see because he's not an Indian player. He was as good as Sachin and Rahul, but never played for India because he was really good. Because at the same time, Rahul and Sachin were playing, so he didn't get the chance. He actually comes out after 25 years. He coaches a women's cricket team and wins the World Cup. People talk about winning the World Cup and trophy. The best photo is this photo, where actually Amol Mazumdar is actually crying and is hugged by 25-year-old woman. And that's what mentorship truly is. Last thing, I know I talked about staircases and trampoline, but I never told you what they are. A staircase is a science process where you think every paper, every award, everything is actually a staircase, and you climb up. Trampoline is where you really have fun. You climb together, you jump together, you not care about how far you have come. So last thing that I want to say is, I hope you choose the trampoline model of doing science. Much more joyful, collaborative, and creative. Thank you.
Thank you so much for this amazing and insightful talk.